Thanks to Henry for putting this together. So I'm in the computer science department, but the data I work with comes from a place that looks like this. Hold on, I'm also getting a phone call. So much like my apartment, the ICU also has a lot of beeping machines, and the doctors contend with a mess of data. This is an actual patient in the neurological intensive care unit at Columbia, where my collaborator is the director. And basically, it's a complete mess, right? To look at this and see patterns and figure out how you're going to treat a patient, what's going on with them, it's almost impossible. This ICU happens to actually store the data, which is helpful. Many ICUs don't, and either you happen to see a number that maybe is useful, or you identify a pattern or something happening, and if you don't, the data's gone forever. So it's quite a challenge. Computer scientists have mostly tried to solve the challenge by telling doctors what's happening. And so triggering an alarm that something bad is happening, or patient's level for something has dropped below a certain value. The problem with that is in the ICU, many bad things are happening, unfortunately, and most of them aren't actionable. And so actually, the number of alarms that you can't do anything about is about 90%. So doctors become immune to them. Like when you get alarms on your phone or notifications, if the information's not interesting or useful to you, you start ignoring it. Right? Computer scientists tried to create alarms with different sounds so that maybe doctors could hear the ones that are important. Turns out doctors couldn't distinguish between the different sounds. And in the worst case, people have actually died because there were alarms that should have been acted on, but doctors ignored them because they're so used to getting information that's useless that they assumed that it was just another false positive and they ignored it. So it's a tremendous problem. And what the doctors really want is to know not just what's happening, but what they can actually do about it. And the big problem on the computational side has been convincing people that that's what doctors actually want. And so there's a lot of focus on prediction. This is one of my favorite quotes. There are lots of others that we could pick on. So this one saying, if you want to do predictions, just don't worry about it. As long as it works, forget about why it works. You don't need to care about that kind of stuff. What's amazing about this one is the author actually was a former Google employee and wrote this a few years after Google's flu was in the news for failing completely. And so if you remember Google flu, at first they were predicting cases of the flu. They were doing a really good job. It seemed to be better than the CDC was doing. And then all of a sudden they start predicting double the number of cases that there actually are, right? And so they're massively over predicting this flu surge that never comes. And the whole reason that they had this error is because they have no idea why the predictions are working. There's no relationship between searching for the flu and actually having the flu. You can search for other people, you search because you hear about a bad flu season on the news. They had keywords like basketball season, things like that aren't really related, but it happens at the same time. And so it's a really weak prediction, right? It's not robust, it's gonna fail unexpectedly, and then you get bad publicity from it because it's based on a correlation and not a causal relationship. And so tried to convince people action requires causality. We need to know why these things are happening, why a patient's having a symptom, right? If we want to be able to intervene and prevent something bad from happening. And the asterisk is more recent work with cognitive scientists showing that causality isn't quite enough. And I'll show you a little bit of that. Right. So one of the data sets I've been most interested in comes from the neuro ICU. We've been looking at stroke patients and basically trying to understand why do some people recover from stroke and others don't? Why do some people regain consciousness and others not? Is there something happening while people are recovering from stroke that we can use to predict who's going to have good outcomes and who's going to have bad outcomes so we can intervene earlier? So we've looked at things like seizures, brain swelling, those kinds of things. It's an interesting data set because the patients are monitored very intensively. And so you don't have that many people, but you have data every 5 seconds during the entire time someone's in the ICU and have to figure out, find the needles in that haystack. However, the data is quite challenging. If you look at what data you actually have, as a researcher, you have no control over what doctors measure. They measure what they think is clinically important or meaningful. So here, purple is the data we don't have for 3 patients. For the second person, purple is almost everything. very little is measured. For other people, you see that monitoring changes over time, right? So as the state of the patient changes, the data we have actually changes over time. For other people, devices are disconnected because you want to, the doctors need to perform a procedure because something broke, right? All these other reasons. So our initial goal was finding causal relationships. We had to solve all these other problems on dealing with, missing data so we don't actually find the wrong causal relationships. And to give a sense of the complexity, it was about a 5-year process from starting this project to finding causal relationships because of all these other problems with this data. I think UA will also talk about complex real-world data. But in the end, we did find causal relationships that were interesting. They were clinically meaningful. I expect absolutely no one here knows what anything on this slide is, and that's perfectly fine. The point is that the causal relationships were changing over time. And so the things that the doctors cared about, which was brain swelling, which here it's TW%, which again means nothing to you, but that's fine. So that the cause of that actually changed during recovery, which means that maybe your interventions for brain swelling also have to change over time. So it was exciting that after 5 years, we found things that we actually trusted, we had causal relationships, they were clinically meaningful. The problem was the entire causal model looks like this. And my collaborator, who's an MD, PhD, an extremely smart guy who has his fingers in people's brains, said that this is an unholy mess. Which is, disappointing after 5 years of life trying to get to this, this one diagram and thinking like I'd solve the problem. But then it got me thinking, is it just him or are other people going to have problems with this, right? My initial goal was we're going to find a causal model, so it's going to help him make a decision. But this actually isn't doing that, right? So when he is deciding how to treat a patient, he can't change someone's heart rate or brain temperature directly, right? The options he has are he can give a medication that can do that, as well as other stuff. But he can't toggle these as knobs. And so it creates a lot of extra work for him to figure out how to behave. And then a few years ago, I started projects with cognitive scientists trying to understand basically how people use information that we get from AI and machine learning to make decisions. The question is, is all the stuff we're doing actually going to help people? And to adjust that, we've been using decisions in familiar scenarios. So the key difference from what's been studied so far in cognitive science is mostly people use very constrained settings like aliens and robots, things you have no experience in, so that you focus on the problem. But when I gave my collaborator information, he's using all the knowledge that he already has. So we're specifically studying cases where people bring their prior expectations and beliefs. So here we have a question about weight loss for a college freshman, give people causal information, either as diagrams or text, and we see what happens. And what turns out is people actually did worse with information compared to nothing. So if you're an optimist, the good news is most people actually know accurate things about weight management. So 89% of our people here got the question right. The bad news is whether we gave them information as a picture or as text, they did significantly worse with more information versus using what they already know. And so it wasn't even just that they were ignoring the information was actually hurting, which was unexpected, right? We mostly think of, information is good, information is power. Actually, what you know can hurt you, it turns out. So trying to figure out, why that's happening, we tested a lot of domains, we kept finding the same thing, information was making things worse. And then the hypothesis was maybe it's happening specifically because people have experience, right? So when people do these questions with aliens and robots, they're fine, and something's going wrong when it's familiar. And actually, it turns out that's the case. And so when people don't have experience, new information is helpful because they're just relying on what we give them, right? They're not trying to figure out how it fits with what they already know, or if they believe it, or thinking that they already have information. The other problem is most of us conflate our experience with knowledge. When we do something often, we think we know something about it. Even if we're not managing our weight successfully or managing our diabetes successfully, the fact that we do it frequently makes us think that we actually have information about it, and it makes us somewhat resistant to new information. So then we thought, okay, people aren't very good at knowing what they know, but maybe we can help people realize what they know. And so we gave people few different options. One was we gave people a quiz. And so you do a true-false quiz with a bunch of true-false questions about diabetes. Sometimes people see their score, sometimes they don't. And the idea is even just doing the quiz, you kind of know if you're guessing and you don't really know anything about the topic, and it might make you more receptive to new information. The other one is we have people rate how much they know about the topic. Then we ask them, okay, sit down, write out the whole process of how people develop diabetes, or how people can manage diabetes with diet and exercise. And then, okay, now rate your knowledge again. And if you do this with stuff you're familiar with, like zippers or toilets, you think you're really confident. Then once you have to write out the whole process, it's like, you have teeth, there's a lever, and then magic happens and the zipper closes. And you don't realize you don't really know that much. And we saw that people, they significantly lower their belief in their knowledge. And our question was, how does that affect how they're going to use information? And so what we find is when they do this self-assessment, basically we see the same drop, that with causal information, people are doing worse. Information is unfortunately harming them. But we don't see the drop in the case where they do the assessment, right? So if you look at the top row, it's basically inoculating people against the negative effects of information. It's not making it better than nothing, but at least it's no longer harmful. Whereas when people don't do the assessment, they have the drop again. And the same thing happened, there's some sort of strange animation. The same thing happens when we give people a quiz. So it doesn't really matter if people were reflecting on their knowledge themselves, or if they're doing a quiz. In both cases, we see exactly the same thing. If they're not doing this reflection and thinking about how much they really know, they do much worse with information. But if they actually do the reflection, the information isn't hurting things. So it's not great news. We haven't been able to make information better than nothing in any case. That's our ongoing work, is trying to figure out what information is useful to which people, how we can make, personalize it potentially. But yeah, it's certainly surprising. And so I'll amend my earlier comment from action requires causality, which I still believe, but that causality alone isn't enough. And that just finding the right causal relationships or true causal relationships isn't enough to help people make correct decisions. We need to know, as people in AI machine learning, much more about how people actually use the output of our algorithms, what level of complexity is actually, are people able to deal with, what information do they need or want to make a decision, what information helps them trust the output of AI machine learning, because clearly the information by itself is not having the intended effect. So I'll stop there and just thank my students and collaborators at a few different universities. And I think we have maybe a few minutes for questions, right, Henry? Oh, Henry, you're muted.
Okay, thanks very much, Samantha. It's very exciting work. Questions from the audience, please? Okay, if not, Samantha, let me just ask your question regarding the approach that you're taking to tackle the current problem in terms of the COVID-19 pandemic. Would there be some also good lessons learned in terms of better prediction, better control of the spread of the virus?
We have ongoing work on how people get information actually during the pandemic. And so looking at where people's information about health comes from, what sources of information they trust. It turns out people put a lot of faith in their own experience, more than a lot of other sources, even compared to like WebMD and things like that, which is somewhat alarming. We experience very few things compared to all the possibilities, right? And people significantly overvalue that. But it's interesting because it provides some ideas about how we could potentially change people's beliefs or correct them if we know where the beliefs are coming from. And then we're currently studying how this changes over time during the pandemic. Their trust in information sources, as well as their beliefs about how you can mitigate COVID, where it comes from, all that. But that's ongoing work, so we don't have a lot of results.
Okay, great. Any questions from the audience again before we move on to the next speaker?
Hi, I had a quick question. That one slide that you showed, my name is Daniel Mufti, by the way. The slide you showed, which had a lot of graphs on it, which you said one of your collaborators said was a bit of a mess. Have you tried presenting data in a different visualization or a different matrix, which is maybe a dimensional model or something like that, which might be easier to look at?
Yeah, so definitely I think there are a lot of opportunities for improving the visualization, right? Here we didn't do very much. And also there's a lot of stuff that's not included in the diagram. We don't talk about the intensity of the relationships or the timing or any of that. I think, yes, it could help. On the other hand, when we've tried both text and diagrams, the results were the same. And so there's something going wrong that doesn't seem to depend on the formatting. The one case that was successful with formatting was we tried complex diagrams where people do even worse than the simple one. But if we highlight the stuff that's relevant in orange, then it was as good as the simple diagram. But again, it's still not better than nothing. So the news is only partially good on that.
Okay, thank you.
Okay, I think an audience submitted a question through the chat icon. And so the question here for you, Samantha, is that I'm learning basic algorithms of ML, machine learning, right now. What are the basic algorithms like KNN that you use in real life problems?
So here, for the most part, we're developing our own approaches. One of the challenges with the health data is it violates many of the assumptions for traditional machine learning algorithms. You can't assume that the data is IID. You have all kinds of complex missingness. Another challenge is, you measure different things for different people. A lot of algorithms assume that you have the same variables for everyone in your study. And so a lot of our work is actually extending existing work to be able to even apply it to this data or developing new things that can actually work on this kind of challenging data.